Hello, this is a good example of always checking your work and never assuming that you've done it right. In my last video, Tommy Gronwald left a message saying that I should not do the 2017 eclipse, and I took that as a challenge. So what I did was I just renamed some of the tabs here. This is the spreadsheet that I made available in the last video. I copied 2024 to 2017 and get the various data points that were pertinent to the 2017 eclipse. And as I was playing around with some of these other columns, I noticed something that didn't quite make sense. That got me on the path of trying to figure out what the problem was. When I made this tab for the 2024 eclipse in the last video, a mistake somewhere around here resulted in me assuming that the moon would have to change height if its diameter remained the same as it was going around, or if it stayed the same height, that the moon diameter had to change accordingly. So one of the very first quick things that I did was I simulated what it should be. If this is the diameter of the path of totality and the sun is of a certain size, and just below the sun is the moon of a certain size, these two lines should represent the edges of totality. And so I followed the idea that if the sun was at a slight angle, as opposed to being directly overhead, how would that change the slope and the size? And I realized that it didn't make much of a difference if it was at an angle or if it was straight down, because we were simply dealing with linear ratios. The ratio between the sun and the moon versus the sun and the ground position of the eclipse totality seems to remain the same regardless of which angle it happens to be. So I created another spreadsheet, and I'm going to make this one available as well. Once again, please feel free to check my math. I started off with wanting to do this in all three dimensions, but then I just very quickly dropped the y dimension, which would be the forward-backward dimension. So you can think of x as left-right and z as the up-down. The way that I did this, I gave it the coordinates in 3D space along with the width of totality. I gave it the coordinate in 3D space for the sun along with the diameter of the sun, and then I proceeded to do a number of calculations. Given the center coordinate of each of the three objects, I calculated the slope between the sun and the point of totality. That gave me a slope, which would essentially be this value right here that you're seeing right down here. And that's this one over here. Then what I did was I calculated the x and the z coordinates based on this angle in 3D space, which would represent this right here. And this angle would be 90 degrees from this one. So this one would be 90 degrees less than this one. And this one would be 90 degrees more than this one. That's these. And then I computed two new slopes, which represent this line and this line. I did something similar for the moon. In this case, I assumed a fixed height and a fixed diameter for the moon. That let me calculate these slopes up to here. And then finally, I subtracted the moon's slope from the sun's slope on either side. And I essentially repeated it for every 10 miles where the sun is not directly overhead of this point. And an initial skim over all of these slopes showed that it was fairly close all the way down. There only seems to be one outlier over here, which happens to be this one as opposed to all of these others. And so with that, I would say that my previous statement where the moon would have to either change size or change height was incorrect, and I am now correcting the record here in this video. So back to my previous spreadsheet. 27 was a copy of 2024 with these values changed and a reworking of the columns pretty much from here on to the end. And then 2024 was basically a recopy of 2017 after I had made all of these modifications with the original data from 2024 copied back into this one. So the progression went copying 2024 to 2017, making a bunch of changes to the various formulas, copying 2017 back to 2024 redo, and then copying the data from the original tab to this new copy. And from that, I was able to recreate new animations, So I'm going to redo the 2024 animation with the corrected values, and I'm also going to show 2017 as well. There's one final thing that I did not mention in the last one. I did create these charts. I was curious to see what the differences were between the expected GP coordinates for the moon compared to the sun to the point of totality versus what it should technically be if the Earth was flat. And in this case, the moon latitude curls up quite a bit over here and then kind of more or less follows fairly close to the expected moon's latitude before veering off again. And that is true for the flat Earth model. You can see that in the animations. This one is for the 2017 eclipse, and this is the one that is for the 2024 eclipse. That's going to be it for now. Thank you for watching. If you liked the video, I would appreciate the thumbs up to subscribe. All that other good YouTube stuff, you know what to do. And with that, I'm going to see you again in another video soon enough. So bye for now.